Tesla is poised to revolutionize its vehicle lineup with advanced battery technology harnessing graphene, promising energy densities that are 5 times higher than standard lithium-ion batteries, capable of storing 1,000 watt-hours per kg. What's more, this battery type boasts an impressive lifespan of 200 years and achieves an energy conversion efficiency of up to 98%. So, what pivotal advancements have positioned Tesla's graphene-based battery at the forefront of the industry? What factors enable a battery to last 200 years? Tesla's advancements in battery technology are evident today with the use of NMC 532 batteries, combining artificial graphite anodes with nickel manganese cobalt. This blend ensures both durability and efficiency, allowing for fast charging without compromising battery integrity, thanks to special additives that manage electrode separation. These batteries can endure up to 10,000 full charge and discharge cycles, equivalent to charging from 0 to 100%. They are projected to power vehicles for over 200 miles, that's 3.5 million kilometers, which equals circling the Earth more than 80 times on a single charge. Incredible. Further studies suggest that careful battery management, such as avoiding full cycles 0 to 100% and instead keeping them between 0 to 80 or 90%, can extend their lifespan to approximately 15,000 cycles. This longevity represents a significant improvement over current battery technologies. These innovations in durable batteries make EVs increasingly appealing to us consumers. Concerns about short battery lifespan are going away. Picture cars fully charged and ready to supply energy back to the grid, a concept known as vehicle-to-grid, which is truly extraordinary. With grid-connected vehicles, EVs can act like mobile batteries, storing surplus energy and returning it when needed, such as at night or on cloudy days. This not only stabilizes the electric grid, but also maximizes the use of renewable energy. It's a significant step towards a greener, more sustainable future. Tesla leads this charge, but they're not alone. Companies like BYD and CATL in China are also advancing, developing batteries capable of lasting from 750,000 to 1 million miles. This technological race benefits all us users. How does exploring the potential of lithium-sulfur and aluminum-graphene batteries contribute to faster and safer charging? Innovations are progressing rapidly, and we'll soon see these technologies on the market. One notable material is lithium-sulfur, which is cheaper and more abundant than traditional materials like cobalt and nickel. This could revolutionize battery production, making them better, more accessible, and environmentally friendly. Lithium-sulfur boasts higher energy density, enabling longer trips or smaller, lighter batteries. These batteries maintain high power percentages even after many rapid charging cycles, making them ideal for various applications, from electric vehicles to solar-powered unmanned aircraft. We can also explore aluminum and graphene, one of the factors that could change the future of batteries. Graphene, a single atomic layer of carbon arranged in a hexagonal lattice, is a 1-atom thick sheet with a relatively large area of 2,630 of a material per unit mass. It exhibits superior charge storage capability that remains largely unaffected during long-term cycling. The bonds within graphene provide it with a tensile strength 4 times of steel, while being exceptionally transparent, flexible, and exhibiting excellent electrical and thermal conductivity. These properties make graphene a suitable candidate not only for batteries, but also for supercapacitors. Graphene-based batteries offer high energy density, capable of storing energy of up to 5,000 watt-hours a kg, which is significantly higher than conventional lithium-ion batteries. This makes them ideal for handheld electronic devices when space is limited. Furthermore, graphene batteries can charge much faster than traditional lithium-ion batteries, with charging rates up to 5C, that's fully charged in about 15 minutes, due to the large surface area of graphene, enabling rapid ion transport. This feature makes graphene batteries ideal for use in electric vehicles, where fast charging is essential. Moreover, graphene batteries have a long lifespan, estimated up to 25 years or 20,000 charge-discharge cycles. This longevity is attributed to graphene's high stability, which helps resist degradation over time, making graphene batteries ideal for renewable energy systems. Additionally, graphene batteries are much safer and environmentally friendly compared to conventional batteries, as they do not contain heavy metals or toxic chemicals. This reduces the risk of harm to humans in the environment and minimizes concerns about thermal runaway, a significant safety issue with conventional lithium-ion batteries. Lastly, graphene batteries boast high power output efficiency, with electrical energy conversion efficiency reaching up to 98%, ensuring rapid and substantial energy delivery. This makes them ideal for high-performance applications like electric vehicles, where high power output is crucial. However, graphene supercapacitors cannot store as much energy as batteries, but they can be fully charged within a few minutes. Therefore, to overcome the low energy density of graphene supercapacitors, scientists have started researching the integration of supercapacitors and batteries into hybrid energy storage systems. In collaboration with Graphene Manufacturing Group, researchers at the University of Queensland, Australia, have developed a prototype hybrid battery based on graphene. This battery utilizes graphene and aluminum as electrode materials and is commonly referred to as an aluminum-graphene battery. It has an energy density of 150 to 160 watt-hours a kg and can charge extremely quickly, like 1 to 5 minutes. Furthermore, aluminum-graphene-ion batteries offer significant advantages in terms of safety, reliability, and longer lifespan over 2,000 cycles, with minimal degradation in terms of performance. According to the latest information, Graphene Manufacturing Group, GMG, has announced the production of aluminum-graphene-ion batteries in pouch form for use in smartphones, tablets, laptops, etc. GMG states that the theoretical energy limit of this type of battery is approximately 1,050 watt-hours a kilogram. Therefore, with further development, we can expect to achieve higher energy densities than commercial batteries soon. When lithium-ion batteries fail, they can potentially catch fire, raising concerns about their use in consumer products. This is due to the flammable electrolyte present in lithium-ion batteries. Nanotech Energy, based in the United States, has developed graphene-enhanced lithium-ion batteries that are non-flammable, safe, and environmentally friendly. They've used graphene as the electrode material in lithium-ion batteries and developed a cost-effective, non-flammable electrolyte called oregano light. These batteries are reported to have an energy density of 162.5 watt-hours a kilogram and can endure over 1,400 cycles, nearly 10 years, with 80% capacity retention. The batteries are completely fireproof and suitable for all weather conditions. In comparison, traditional lithium-ion batteries can only endure 300 to 500 cycles, about 2 to 3 years. According to latest updates, the company has started accepting pre-orders, and the batteries can be customized for use in electric vehicles, computers, and military applications. Tesla recently announced that their Model 3 battery has an energy density close to 260 watt-hours a kilogram. However, it requires a complex cooling system to avoid overheating, thus taking up a significant amount of space. On the other hand, graphene batteries do not overheat or explode, eliminating the need for a cooling system and allowing this space to be used for energy storage in electric vehicles. A breakthrough in graphene battery technology occurred when GAC Motor Company Limited, a Chinese automaker, unveiled the Aeon 5 electric car, equipped with graphene batteries capable of a 1,000-kilometer range and can recharge up to 80% capacity in only 8 minutes. There's no doubt that the commercialization of graphene batteries is underway and will soon outperform conventional batteries when widely applied. What most people are interested in is that these batteries have 3 times longer lifespan and 7 times faster charging capability compared to traditional lithium-ion batteries. By using abundant and inexpensive materials like natural gas and aluminum, these batteries could be a game-changer in the electric vehicle market. Besides being faster and more durable, aluminum graphene batteries are safer, less prone to overheating, and do not require complex cooling systems, helping reduce weight and costs. What's even more fantastic is that about 90% of aluminum can be recycled. The manufacturing process of these batteries also produces hydrogen as a byproduct, which can be used in the hydrogen transportation industry, promising a greener and more sustainable future. Looking at these advancements, the future of electric vehicles and other electric devices becomes incredibly bright. Technologies like longer-lasting and more efficient batteries not only improve our daily lives, but also bring us closer to a sustainable future. Recently, GMG has been planning to test prototype fuel cell vehicles within the next 6 to 18 months, marking a significant step towards the future. Another promising innovation comes from MIT researchers who accidentally discovered a strong aluminum-sulfur battery that's 6 times more powerful than lithium-ion batteries and can be fully charged in less than a minute. This is truly revolutionary. Imagine charging your car in seconds. The cost of these batteries is estimated to be about $8.99 a kilowatt-hour, a fraction of the current cost of lithium-ion batteries. The simplicity of the chemistry used also promises increased recyclability of these batteries at the end of their life cycle, marking a significant step towards a sustainable future. With all these innovations, we're witnessing a true technological revolution. Aluminum and graphene batteries, along with aluminum-sulfur batteries, promise to transform the energy and electric vehicle industries. These new technologies not only promise to revolutionize the automotive sector, but also open up new possibilities in large-scale energy storage, contributing to a broader shift towards a cleaner and more efficient energy source. The The combination of lightweight design, long lifespan, and competitive pricing is truly groundbreaking. Imagine a world where electric vehicle batteries not only last longer, but are also safer and more environmentally friendly. These batteries can be efficiently recycled, reducing environmental impact and eliminating dependence on expensive and scarce materials like cobalt and nickel, replacing them with abundant and cost-effective alternatives like aluminum and graphene. These batteries not only have a longer lifespan, but also charge faster, helping reduce costs and improve sustainability. Meanwhile, lithium-sulfur batteries promise superior energy density, enabling longer trips with smaller and lighter batteries. These innovations are on track to transform the electric vehicle industry, making it more accessible, efficient, and environmentally friendly. Elon Musk and Tesla are heavily investing in these technologies, and they're not alone. Major automakers like Ford and Mercedes-Benz are also exploring solid-state batteries through partnerships with battery manufacturers. The race is on, and we, as consumers and the environment, we're the winners. When will we see these batteries on the market? Optimistically, some of these technologies could be available in less than 5 years, a short time frame considering the positive impact they could have on our lives. The transition to more efficient and sustainable batteries is closer than ever before. How can vehicle-to-grid VTG technology transform energy consumption levels? Allowing electric vehicles not only to consume energy but also to supply it back to the grid is an efficient method of utilizing energy from electric vehicle batteries when they're not in use for driving. This technology, known as vehicle-to-grid (V2G), is being integrated into modern smart grid systems. When electric vehicles are inactive, V2G enables them to feed energy back into the electrical grid, helping to reduce grid loads and balance energy demands. This not only increases the readiness of the grid system, but also optimizes the use of renewable energy sources and minimizes emissions. Researchers and tech companies are advancing solutions to make V2G an integral part of the transition to clean and sustainable energy. That requires a lot of energy. The country will need to generate approximately 2.5% more electricity to support this large-scale electrification of vehicles. However, this can be achieved with careful planning, demand response, peak demand management, and the increasing deployment of renewable energy sources. Grid operators need to modernize and decentralize the grid quickly. For example, they could enable millions of homeowners with solar panels to supply electricity and store any excess energy. EV chargers also need to be flexible. If everyone plugs in their EVs at home during the peak hours from 5 to 7 p.m., the grid could get overloaded and experience blackouts. Smart charging, where software determines the optimal time to connect and charge vehicles, is crucial in this scenario. The V2G technology offers significant financial benefits, especially for electric vehicle (EV) owners and fleet operators. Research indicates that cost savings in electricity system operation can reach up to £15,000 per year per electric vehicle, with CO2 savings averaging about 60 tons per year per vehicle. The annual financial benefits of V2G charging range from $875 to $1,560 a vehicle. Furthermore, V2G can save consumers a substantial amount annually, with potential savings of up to £300 a year. These savings are achieved through smart charging and selling surplus electricity stock back to the grid, net metering. This approach also helps significantly reduce future grid upgrade costs, with potential savings ranging from €0.5 billion, that's 450 million Great British pounds, to €1.3 billion, 1.2 billion GBP annually. Moreover, electric vehicles can store surplus energy generated from renewable sources such as solar panels and wind during low-demand periods and supply this energy to the grid during peak demand. This capability supports the grid in managing energy supply more efficiently and reduces dependence on fossil fuel-based generation, promoting cleaner energy structures. The flexibility provided by V2G technology can significantly reduce the need for investments in low-carbon emission generation, thereby supporting national carbon reduction goals. What is Tesla's role at the forefront of the battery revolution? Tesla's battery technology has undergone remarkable development since its initial stages. It all began with the iconic Tesla Roadster, the company's first electric vehicle, showcasing the potential of electric mobility. With the success of the Roadster, Tesla pushed the boundaries further by introducing the Model S sedan, setting new standards in range and performance in the EV market. As Tesla's ambitions grew, so did the demand for increased production capacity, leading to the establishment of gigafactories. These state-of-the-art facilities enabled Tesla to scale up battery production and meet the growing demand for its vehicles. Tesla's consistently focused on improving energy density, allowing its batteries to store more energy while delivering enhanced range and performance. These advancements in energy density have been instrumental in making electric vehicles more practical and appealing to a broader consumer base. The chemistry of Tesla's lithium-ion batteries plays a crucial role in their dependency and performance. These advanced batteries use lithium ions to efficiently store and release energy, making them ideal for electric vehicles. Tesla's battery pack architecture is meticulously designed to optimize space utilization and ensure safety. By strategically arranging battery cells and modules, Tesla maximizes available space within vehicles while maintaining structural integrity and minimizing the risk of thermal runaway. Thermal management systems play a crucial role in maintaining the efficiency and longevity of Tesla's batteries. Tesla employs advanced cooling and heating techniques to regulate the battery pack temperature, ensuring optimal performance in varying weather conditions. Tesla's commitment to advancing battery technology extends beyond electric vehicles, encompassing a range of improved solutions for energy storage across grid-scale applications, commercials, and industrial sectors, as well as residential applications. Megapacks, Tesla's grid-scale energy storage solution, provides sustainable and reliable energy storage for renewable sources, ensuring stable energy supply even during peak demand periods. Powerpacks serve the need of commercial and industrial sectors, offering scalable energy storage solutions to enhance efficiency and reduce costs. For residential use, Tesla's Powerwall provides homeowners with a compact and efficient energy storage system, allowing them to optimize energy consumption, increase self-sufficiency, and have backup power during outages. Tesla's supercharger network has revolutionized the electric vehicle charging experience, enabling fast and convenient charging at multiple locations worldwide. Tesla's impact on the energy landscape extends beyond advancements in battery technology. The company is actively pushing forward the transition to electric vehicles, aiming to revolutionize transportation by offering sustainable and high-performance electric cars. By providing innovative electric vehicle models and expanding charging infrastructure, Tesla is making electric mobility more accessible and appealing to a broader audience. Tesla's integration of renewable energy plays a crucial role in balancing supply and demand. By combining Tesla electric vehicle charging with renewable energy sources such as solar and wind power, Tesla promotes the use of clean energy and reduces dependence on fossil fuels. This integration contributes to creating a more sustainable and flexible grid, ensuring stability even with increased penetration of renewable energy. With these revolutionary advancements in graphene-based technology, Tesla is expected to integrate them into their upcoming models. These new batteries promise to power future Tesla vehicles with unprecedented efficiency and longevity, potentially enhancing performance across their entire lineup from sedans to SUVs and beyond. This integration underscores Tesla's commitment to pushing the boundaries of electric vehicle technology while reinforcing their position as a leader in sustainable transportation solutions. We hope you'll experience the utmost relaxation after watching this video. If you do, please hit the like button and join the Tesla Car World community by subscribing to our channel. Hit the notification bell icon to stay tuned for any fantastic videos coming your way. Your feedback and time are highly appreciated. EV expert Sandy Munro once remarked that solid-state batteries are the kiss of death for gasoline and diesel, meaning they pose a significant threat to Tesla's 4680 batteries. With the superior power of solid-state batteries, Toyota is confident it can regain its lost position from Elon Musk, boasting a range of 700 miles and a full charge in 10 minutes. If these criteria are met, solid-state battery cells will be a major breakthrough. However, solid-state batteries still face a significant issue. So between Tesla's 4680 batteries and Toyota's solid-state batteries, who's going to be king? Tesla is achieving rapid production progress with a 4680 battery, producing around 140,000 cells per day at the Giga Texas facility. Currently, with Toyota's solid-state batteries not yet on the market, the 4680 battery remains the best available exclusively from Tesla, with no worthy competitors to make Elon Musk truly concerned. But let's imagine the scenario when solid-state batteries hit the market. Will the 4680 become overshadowed? Let's compare them now. We think we should still understand the concept of these two batteries first, because that is the root of the problem. We will explain as briefly as possible. First is the solid-state battery. This is still a battery with 4 components: anode, cathode, plastic polymer separator, and electrolyte solution. However, what makes it a breakthrough to be considered the 4680 killer is the transition from a liquid electrolyte solution to a solid electrolyte solution. Liquid electrolyte solution is found in any other lithium-ion battery. That's the knowledge of solid-state batteries. We think you have understood it. Meanwhile, the 4680 battery was first announced by Elon in September of 2020 and set to begin production the following year. The Tesla 4680 battery remains a cylindrical lithium-ion type with a diameter of 46 millimeters and a height of 80 millimeters. The cathode of the 4680 is predominantly nickel, making up 81.6%, with the remaining 20% consisting of lithium and cobalt. The anode uses silicon instead of graphite, and the cell's characteristics indicate very good technical specifications. But that's not all. What makes the 4680 battery even more special is its use of a tabless electrode design, which eliminates the tabs that connect the two poles of the battery. This design helps increase energy density, reduce internal resistance, and simplify the manufacturing process. Both batteries are constructed using technologies that significantly impact energy density. Solid-state batteries with solid electrolytes still need to efficiently conduct lithium ions between flexible cathodes and anodes. On the other hand, the 4680 battery features a structural design and composition that swiftly affects the lithium transport process. So, who will win in energy density? There's no denying that the race in modern battery technology is increasingly fierce, with energy density being the foremost factor driving competition. High energy density means batteries can store more energy in the same volume or weight. Therefore, electric vehicles can travel longer distance before needing to recharge. In the Tesla 4680 battery, the energy density has reached 244 to 296 watt-hours a kg, compared to 200 watt-hours per kg in a typical lithium battery, which means it has improved the energy density by more than 20%. Tesla announced that the 4680 battery will increase the range of electric vehicles by 16%, and combined with the cells-to-chassis technology, the packaging technology helps increase the range of vehicles by 14%. Finally, we will have nearly a 30% range improvement. For easy illustration, consider this example. In the case of a Tesla Model 3 with a 75 kilowatt-hour battery pack using traditional LFP batteries, it would typically achieve a range of about 350 miles or 560 kilometers and weighs approximately 4,000 pounds or 1,800 kilograms. However, if this sedan were equipped with a battery pack of the same size but utilizing 4680 cells, it could potentially achieve a range of around 406 miles or 653 kilometers and the weight cut to approximately 3,600 pounds. This means that the 4680 battery can store more energy per unit volume or weight compared to other types of batteries, resulting in longer driving ranges and lower battery weights for electric vehicles. Currently, Tesla is only using the 4680 battery for the Cybertruck, and the performance for this pickup truck is also extremely impressive. So what about the energy density of Toyota's solid-state battery? While Tesla's 4680 battery pack only aims to surpass most of its competitors' electric vehicles in terms of performance, Toyota is determined to have an electric vehicle with a range comparable to internal combustion engine vehicles with solid-state batteries. You know, with these things that haven't been released, whatever the manufacturer announces is assumed to be true. According to our understanding, Toyota plans to increase the energy density of solid-state batteries to more than double the energy density of current lithium batteries by 2025, reaching 450 watt-hours a kg. This advancement would allow for storing more energy with the same weight. If the Japanese automaker achieves this ambition, it means the energy density of solid-state batteries would be 1.8 times higher than that of the 4680. Consequently, it suggests that the driving range of Toyota's electric vehicles using solid-state batteries will increase significantly compared to Tesla's EVs. If you look on the internet, Toyota plans to use solid-state EV batteries with a range of 750 miles, which means 1,200 kilometers. With this range, Toyota is confident that it'll catch up with Tesla in an effort to regain its lost position. Especially, the Japanese electric car manufacturer also wants to prove that Tesla's 4680 battery is not something to be proud of. Most recently, we also received some sources saying that Toyota is also planning to develop solid-state batteries for EVs with a range of up to 923 miles, equivalent to 1,500 kilometers. It's hard to believe, but if this happens, Tesla could be in big trouble. From a scientific perspective, it's evident that solid-state batteries have the potential to dominate the market in the future over Tesla's 4680 battery, mainly due to their significantly superior energy density. However, it's crucial to understand that higher energy density in batteries doesn't necessarily mean faster charging times. So, how do the charge times of the 4680 battery and Toyota's solid-state battery stack up against each other? Regarding charging speed, according to insiders at Toyota, the prototype solid-state battery has a clear advantage over current lithium batteries in terms of charging speed ranging from 0 to 100% in just 15 minutes. Therefore, customer concerns about hours-long charging times may soon be a thing of the past with solid-state batteries. Toyota's promised charging time is nearly comparable to the LFP cells from Shenzhen recently announced by Kata, which boast extremely fast charging speeds. However, in our opinion, Toyota's solid-state batteries have more trouble achieving these charging speeds. While most batteries can be fast charged at least a few times, applying a lot of power is very harsh on them. This is why the trickle chargers found in many people's garages are surprisingly slow. If someone fast charges their battery frequently, the internal structure of the battery tends to fail after a disappointingly short time. All lithium-ion batteries suffer from dendrite formation, but this happens very quickly in solid-state batteries. Dendrites are like branch formations that can spread between batteries' electrodes, causing them to short circuit. Until now, it was a mystery how soft lithium dendrites could penetrate through the hard layer of the solid electrolyte. To put it simply, frequent fast charging will cause solid-state batteries to short-circuit easily, reducing battery performance faster than a regular lithium battery with a stable charging rate. So is the 4680 Tesla battery better? With a 4680 Tesla battery, we found that the anode and cathode terminals of the 4680 battery use full polarity tabs, which means that the full polarity tabs will greatly increase the path of the current and make it easier for the electrons to move inside the electrons. That makes the internal resistance of the 4680 battery only 1/5 that of the 2170 battery. Therefore, the estimated charging speed of the 4680 battery will be many times faster than a conventional lithium cell. According to the actual test report, it only takes 20 minutes to charge the 400-volt 4680 battery system to 60%. In the case that the 4680 battery is combined with an 800-volt voltage system, the charging speed will be many times faster. Currently, the Cybertruck using the 4680 battery pack achieves a 40-minute charging speed from 10 to 80% with a fairly large battery pack, 123 kilowatt hours. Previously, in addition to the Cybertruck, a few Tesla Model Ys were also equipped with a 4680 battery pack and provided incredible charging times. One owner drove the SUV to a supercharger station in California when the car was completely out of battery and couldn't move it any further. In just 32 minutes, the car was charged to 80% of its battery capacity via a 250 kilowatt charger. It's undeniable that the charging speed promised by Toyota's solid-state batteries has yet to surpass Tesla's 4680 cells. This could make impatient customers less enthusiastic about waiting for electric vehicle charging times to become more enjoyable. However, that's not the whole story. If you desire a longer battery lifespan and safety, Tesla's 4680 cells have an advantage over solid-state batteries due to their stable charging speed. Toyota's solid-state battery seems to have two pretty good advantages to surpass the 4680 Tesla. Both energy density and charging time are enough to top the entire industry, but in the end, the cost to produce this type of battery is a nightmare for manufacturers, even a factor preventing it from launching on the market. So, why are solid-state batteries so much more expensive than Tesla's 4680 cells? Talking about a not-yet-launched battery technology being more expensive than a widely produced type of battery may seem contradictory at first glance. However, considering the significant delay since the initial mention of solid-state battery development back in 2020, now nearly 5 years ago, it still doesn't exist. From what we understand, solid-state batteries do not completely eliminate lithium. In fact, some research suggests that solid-state batteries can use lithium in amounts that are 5 to 10 times higher than that in 4680 batteries. The price of Toyota's solid-state batteries is estimated to range from $800 per kilowatt hour to $400 per kilowatt hour by 2027. With liquid electrolyte batteries currently costing around $156 a kilowatt hour, that creates a significant manufacturing cost issue. Toyota's solid-state battery is expensive because it's been reported that the battery uses no liquid electrolyte to transfer energy from the cathode to anode, or vice versa. There has to be a solid electrolyte to take its place. Materials for this type of technology are scarce and very expensive. On top of that, there's no standardization material that's used in the manufacturing process and no standardized process in which they're made. This makes them extremely hard to mass produce. Some estimates put solid-state batteries at 3-4 times the price of traditional lithium-ion batteries. These costs can add up when you're talking about a vehicle that can already cost as much as $200,000 for a top-of-the-line model. Are the savings worth the added mileage and faster charging? That's for the consumer to decide, and presumably they're going to get their chance. Meanwhile, Tesla's 4680 battery, leveraging a production process controlled by Tesla, aims to reduce costs significantly. The company forecasts a 56% reduction in cost per kilowatt hour and a 69% reduction in capital investment per kilowatt hour. Although specific cost details for the 4680 battery are not disclosed, analysts predict current prices ranging from $114 to $170 per kilowatt hour. Elon has set future goals to scale 4680 battery production to 1,000 gigawatt hours per year, with costs potentially dropping to $70 a kilowatt hour, a challenging but ambitious target. Tesla continues to push forward aggressively and has achieved surprising speed in this endeavor. According to Tesla's VP, Lars Moravi, the company expects their 4680 battery cells to become cheaper by the end of the year by reducing the cost to nickel suppliers. Now, for safety, which battery technology is considered safer for electric vehicles? Tesla's 4680 battery is highly regarded for its safety due to several prominent advantages. Firstly, its simple design eliminates tab connections, reducing the risk of short circuits and enhancing system stability. Secondly, the thicker steel shell provides better protection for the battery cells against impacts and vibrations, thereby increasing durability and safety. Finally, the integrated cooling system of the 4680 batteries helps efficiently control temperature, minimizing the risk of combustion. However, this isn't the biggest advantage of the durability that the 4680 battery provides. Perhaps you didn't know, due to its higher mechanical durability, the 4680 battery is better suited for cell-to-chassis technology. Specifically, Tesla has eliminated the battery pack lid on the 4680 cell, increasing space utilization. In terms of manufacturing costs, Musk mentioned that after implementing the integrated CTC Plus mold casting technology, it could save 370 parts, reduce vehicle body weight by up to 10%, and lower battery costs per kilowatt hour by 7%. On the other hand, Toyota's solid-state battery technology is also considered a safe battery technology because transitioning from the liquid electrolyte of lithium-ion batteries to a solid electrolyte helps reduce the risk of leakage. In lithium-ion batteries, the liquid electrolyte allows lithium ions to move between the positive and negative electrodes during the charge and discharge cycles. However, like any other liquid, this electrolyte layer is sensitive to temperature changes. You might have seen batteries swell in the middle or even leak some electrolyte fluid. That's really bad. If the electrolyte vaporizes or leaks out, it can create a short circuit between the positive and negative electrodes, potentially leading to fires or explosions. If that starts to happen under your car's floor, you're in for a really bad day. So in summary, Toyota's shift to using solid electrolytes will make electric vehicle safety much less risky. With the initial development of solid-state batteries, Toyota researchers have emphasized maintaining temps between 50 to 60 degrees Celsius for optimal performance, and expect to surpass these figures as they upgrade to more heat-resistant electrolytes. Real-world tests comparing solid-state batteries and lithium-ion batteries of the same volume have shown that solid-state batteries have relatively low flammability and relatively high electrochemical stability. However, as mentioned earlier, solid-state batteries are prone to rapid and more frequent dendrite formation compared to the 4680 battery, which poses a challenge. Additionally, recent tests have indicated that they can still catch fire when severely crushed or punctured. This means that even with solid-state batteries in electric vehicles, if a serious accident occurs and the battery pack experiences a significant impact, the risk of fire remains present. Tesla's new 4680 battery cell represents a significant advancement. Not only is the cell larger, but its internal structure is also distinct. Meanwhile, solid-state batteries have long been touted as a great application to unlock the potential of electric vehicles. With their lighter weight, higher efficiency, and faster charging times compared to lithium-ion batteries, solid-state technology is being heavily promoted. Toyota alone holds over 1,600 related patents in solid-state battery technology, underscoring their success once again in the laboratory. But how does that become a viable and achievable means? The answer is probably certain. Currently, most car manufacturers have plans to introduce solid-state battery electric vehicles to the market by the end of this decade or later. This leaves ample time for speculation and bold claims without any specific support for them. At this point, most people are aware that electric vehicles are expected to have longer lifespans than traditional internal combustion engine vehicles. Currently, governments require electric vehicles to have warranties of 8 years or 100,000 miles. California's gone further, setting requirements of 10 years or 150,000 miles. Toyota plans to maintain over 90% solid-state battery efficiency after 30 years of use. If this technology can be realized sooner rather than later, the cycle efficiency will exceed Tesla's million-mile battery capacity. Meanwhile, the Tesla 4680 battery is predicted to achieve a lifespan of over 1 million miles, equivalent to 16 years of use if driven an average of 40,000 miles per year, and depending on maintenance levels. We hope this information is accurate. However, this is only a prediction based on initial test data, and actual lifespan may vary depending on several factors. Usage factors such as fast charging, high-speed driving, and harsh climate conditions can reduce battery life. Proper maintenance, including software updates and regular checkups, can help extend battery life. Additionally, environmental factors like extreme temperatures can also impact battery lifespan. The debate between solid-state batteries and Tesla's 4680 will ultimately take some time to get to a final answer. Electric vehicle batteries are complex, and it's still unclear which technology will meet the needs of the market. Some love a battery pack that offers superior performance, but the majority of others prefer cheaper battery packs instead of expensive ones. While the 4680 is the top choice for Tesla and is expected to be applied in many Tesla models in the future, Toyota is still focusing on accelerating the launch of solid-state batteries by 2027 with many promises to change the game. In addition, many other battery technologies such as sodium-ion batteries, LFP, solar batteries also have similar improvements. So, what do you think about the 4680 Tesla battery and the Toyota solid-state battery? Which one will win the race? Drop a comment below. We hope you'll have the most relaxing feelings after watching this video. If you did, please hit the like button and join the Tesla Car World family by subscribing to our channel. And don't miss out on any of our awesome videos by hitting the bell icon. We value your feedback and your time. The ultra-dense battery technology, boasting an impressive energy density of up to 500 watt-hours per 1 kilogram, presents a superior solution for everyday consumers, achieving an 80% charge in less than 6 minutes. This addresses one of the most common and practical concerns regarding electric vehicles, significantly reducing the gap between refueling a gasoline vehicle and recharging an electric one. Could this groundbreaking battery technology potentially revolutionize the world? How does ultra-dense battery technology transform the electric vehicle industry? We know that many are unaware of this new type of battery and its origins. Well, Amprius, a startup from Stanford University based in Fremont, California, is the driving force behind it. They are pioneering the idea of lithium-ion batteries by replacing a small but crucial component with a widely available material, resulting in significant advancements. What is that component? In ultra-dense battery technology, using silicon instead of traditional graphite is a significant breakthrough. Silicon, often in nanowire or other nanostructures, enhances lithium-ion storage capability, being able to store over 10 times more ions than graphite. However, volume expansion during charging and discharging reduces silicon's efficiency. A solution is silicon nanowire technology, which addresses volume expansion issues and improves battery durability and lifespan. For the cathode, both traditional and advanced battery materials like lithium cobalt oxide and sulfur are utilized in lithium-sulfur batteries. In electrolytes, both liquid and solid forms can be used, with solid electrolytes often preferred in ultra-dense battery designs to enhance safety and energy density. Lastly, separators in ultra-dense batteries are commonly made from polymer or ceramic materials, aiding in preventing short circuits and controlling lithium-ion flow within the battery. Amprius has identified the positive or carbon electrodes as the Achilles heel of batteries, which are easy to repair but view silicon as the perfect stationary material. Silicon stores lithium much better than lead, with a single silicon atom capable of storing 4 lithium ions. Just that alone means silicon-positive electrodes have up to 24 times higher efficiency than conventional lead-positive electrodes. It also allows silicon anode batteries to have nearly 10 times higher energy density than conventional lithium-ion batteries with lead or carbon-positive electrodes. Higher density equates to fewer batteries. In other words, less battery weight is needed to achieve similar performance. The positive electrodes made of lead or carbon in lithium-ion batteries are crucial, essentially the heart of the battery. Although they enable everything to function, they're seen as not very efficient. In lithium-ion batteries, the electrolyte carries lithium ions from the positive carbon or lead electrode to the negative electrode. It's important to note, both positive and negative electrodes store lithium. It takes 6 lead atoms to store 1 lithium ion during charging, through a process called intercalation. This is a significant bottleneck that lithium batteries can achieve, and many electric vehicle manufacturers are grappling with it, including Tesla. So why do many battery manufacturers not use silicon? Firstly, silicon is perhaps too good at storing lithium. It tends to absorb so much lithium that it can swell up to 3 to 4 times its volume during charging. This swelling phenomenon, after just a few charge-discharge cycles, can cause the positive electrode to crack and eventually destroy the battery. Therefore, we often see a small amount of silicon mixed into their standard carbon-positive electrodes, just enough to enhance their performance without causing swelling issues. The tech giant Tesla previously stated back in 2020 at their Battery Day event about their efforts to incorporate a small amount of silicon into their latest battery type. Amprius's nanotechnology develops silicon nanowires directly from the current collector, then coats them with silicon to form a positive electrode resembling a forest of trees. The result is a geometric structure almost made entirely of silicon. This helps ions and electrons move much more easily as they can travel shorter distances, improving charging and discharging times. The nanostructure also provides more surface area than lead, further enhancing energy density. And of course, it also addresses the silicon swelling issue. By using a nanowire form factor, there's enough space between the wires to accommodate volume expansion, making the positive electrode much more durable. Not to mention, the thinner configuration makes it flexible enough to bend within the substrate. Typically, scaling up such nanotechnology solutions is very challenging. After all, we're talking about silicon nanowires that are a few microns in size, smaller than the width of a human hair. Moreover, to reap all these amazing benefits, you need to figure out how to turn these small structures into big outputs. Amprius hopes to tackle this issue by collaborating with the Dutch company Centrotherm. They have decades of experience in scaling materials for the semiconductor and solar energy industries. Their pilot scale-up process aims to achieve lower production costs and higher yields by producing Amprius's high-energy density, reliable, and potentially cheaper rolled-form batteries. But how do the numbers stack up? Amprius's batteries boast an energy density of 500 watt-hours a kg or 1150 watt-hours per liter, over 50% better than some of the best lithium-ion batteries on the market. Amprius also claims a high energy density of up to 10 C compared to the typical 3 C of lithium. Rating C is a measure of the speed and safety of battery charging and discharging. The higher the C rating, the faster the charging and discharging speed. This not only affects the charging time of the battery, but also the speed of energy released for high-intensity applications. And the most amazing thing for ordinary customers is that this battery can reach 80% charge in less than 6 minutes. One of the most common and practical complaints about electric vehicles is that charging the battery takes more time than filling up a gas tank. If the Amprius battery can be charged in just 6 minutes, the gap between refueling a gasoline vehicle and recharging an electric vehicle will soon become quite small. In addition to the technology, silicon has some economic benefits. Unlike some other proposed battery materials, silicon is not the next generation expensive or difficult to produce alloy. It's actually the second most abundant element on Earth. This will help reduce battery costs and ensure no supply chain issues. For comparison, 90% of the world's lead comes from one region in China, which could pose a significant supply chain risk. Silicon may also have environmental benefits, as recent studies have shown that mining and smelting lead are not the best for the environment. Lead smelting is an energy-intensive process and still relies on some of the dirtiest fossil fuels. Studies have shown that emissions from these processes are worse than we previously thought, by 4 to 10 times, so perhaps we should use silicon-positive electrodes and hurry up. In your opinion, do you anticipate that any other comparable companies will prioritize silicon to stand out in light of these future prospects of battery technology? If so, kindly reply with yes or otherwise type no in the comments so we can know. How do ultra-dense batteries compare with traditional batteries? We appreciate this ultra-dense battery as it represents a significant leap in energy storage, addressing many limitations of traditional lithium-ion batteries. One of the top concerns with conventional batteries is their limited energy density, typically ranging from 150 to 250 watt-hours a kg, lower than fossil fuel energy densities. This severely limits the range electric vehicles can achieve on a single charge. Additionally, the long charging times of traditional batteries, ranging from 1 to 12 hours depending on the charger type, are inconvenient compared to the mere minutes it takes to refuel gas or diesel-powered vehicles. This is one of the many constraints that make users hesitate to switch to electric vehicles. On the contrary, the ultra-dense battery showcases an impressive energy density, ranging between 3 to 500 watt-hours a kilogram, which is double the capacity of traditional lithium-ion batteries. This enhanced energy density allows for storing more energy within the same weight, enabling electric vehicles to travel longer distances on a single charge. Furthermore, with a volumetric energy density exceeding 1,500 watt-hours per liter, the ultra-dense battery conserves space and facilitates the streamlined design of compact energy storage systems for various companies. When evaluating the lifespan and performance of traditional lithium-ion batteries, they typically only manage between 500 to 1,000 charge cycles before experiencing significant power degradation, necessitating cost replacements after a few years of usage. Additionally, there are safety concerns such as the potential for electrolyte leakage and overheating, which could lead to explosions, thereby mandating the implementation of rigorous thermal management systems, thereby adding to the complexity and expense. In contrast, The ultra-dense battery can sustain excellent performance after enduring 1,000 to 3,000 charge cycles, significantly outlasting traditional counterparts. This prolonged lifespan aids in diminishing the need for frequent battery replacements, thereby reducing costs for end users. Innovations in materials and technologies such as silicon anodes and graphene contributed to heightened mechanical and chemical resilience, ensuring consistent performance throughout the battery's operational life. These batteries are also engineered to expedite charging speeds, capable of reaching full charge within approximately 15 minutes to an hour as opposed to the 1 to 4 hours required by traditional lithium-ion batteries, substantially cutting down on charging duration and enhancing user convenience. Furthermore, these batteries mitigate the associated risks of fire and explosions, further bolstering safety measures. Ultra-dense batteries, apart from notably enhancing performance, also bolster user safety by reducing the risk of hazardous incidents. Unlike conventional lithium-ion batteries, which raise significant environmental concerns due to the extraction of resources like lithium, cobalt, and nickel, ultra-dense batteries employ advanced materials that diminish dependence on rare and environmentally harmful metals. The extraction of these resources often involves extensive mining and substantial environmental repercussions. Furthermore, the recycling practices associated with lithium-ion batteries are ineffective, resulting in considerable waste pollution. Conversely, ultra-dense batteries are designed with environmental friendliness in mind, facilitating easier recycling and reducing electronic waste. Silicon, one of the key components in ultra-dense batteries, is abundant and simpler to produce, being the second most abundant element on Earth. This contributes to reducing battery production costs and ensuring a secure supply chain. In contrast, 90% of the world's lead supply originates from a single region in China, posing significant risks to the global supply chain. Traditional lithium-ion batteries exhibited diminished performance under extreme temperature conditions, with efficiency and lifespan significantly declining at temperatures below -20 degrees Celsius and above 60 degrees Celsius. In contrast, ultra-dense batteries are engineered to function effectively in both low and high temperatures, mitigating performance degradation. For instance, solid-state battery technology can operate effectively at temperatures as low as -30 Celsius, while maintaining stable performance at high temperatures, thereby enhancing efficiency and durability in challenging environments. Last but crucially, when comparing manufacturing costs, solid-state batteries often have a higher initial cost compared to conventional lithium-ion batteries. The manufacturing cost of solid-state batteries can range from $120 to $150 per kilowatt hour. For conventional lithium-ion batteries, that typically ranges from $100 to $130 per kilowatt hour. Although there is a difference in initial manufacturing costs, when considered the cost per charge, we see a different picture. The cost per charge of solid-state batteries is often higher than that of conventional lithium-ion batteries. For example, to charge 1 kilowatt-hour of energy, the cost can range from 12 to 15 cents for solid-state batteries, while conventional lithium-ion batteries may only range from 10 to 13 cents. Although the initial manufacturing cost of solid-state batteries could be higher, recharging costs may be higher during usage. What immediate challenges are manufacturers facing with ultra-dense batteries? However, why are these advancements crucial? What can we do with batteries boasting higher energy density? Well, as we've hinted several times, this could mark a significant leap forward for EVs. In terms of a vehicle performance, Amprius' electric vehicles could charge in just a few minutes and have a faster 0 to 60 acceleration time. It could even pave the way for larger electric vehicles like trucks and commercial aircraft, although currently it's just potential speculation. And while not as flashy as high-performance electric vehicles or some other feasible applications, silicon anode batteries could be very convenient for wearable devices and consumer electronics. Just imagine a smartphone or laptop charging to full capacity within just a matter of minutes and lasting much longer. Amprius' nanotechnology allows its batteries to overcome the swelling issues of conventional silicon anodes, which have been a major drawback. Silicon anodes are currently more expensive to produce than lithium anodes because they require specialized equipment and techniques. Moreover, creating complex nanostructures is much more challenging than manufacturing standard wires. Standard wires are drawn through molds to achieve smaller sizes, while nanowires must be developed directionally from vapor, sol gel, or electrochemical processes instead of being drawn out like regular wires. So, while silicon may be abundant, the production process is a limiting factor that could make these types of batteries too expensive for widespread use beyond the most demanding applications at present. And although to date, Amprius's batteries have performed well in lab and field tests, nanotechnology might be challenging to scale from the lab to meaningful real-world applications. As we noted earlier, Amprius is actively working to address this issue with their pilot scale rolling process. But can they do that at a reasonable cost over time? Furthermore, Amprius's technology requires proprietary anodes that are currently incompatible with existing large-scale EV battery manufacturing plants. This is partly why Amprius's current strategy is focused on niche markets like unmanned aerial vehicles. If successful, they could ramp up production, reduce costs, and begin expanding into the consumer electric vehicle market. Even if everything works perfectly, it'll still take some time before you can buy an EV with long-range, fast-charging capabilities featuring Amprius batteries inside. However, with all the promising analysis of the ultra-dense battery discussed above, it seems to be teetering on the edge of being too good to be true. Could this be a case of being too good to be true? While the technology has been previously tested by Mobile Power Solutions, a leading tester, it'll require further verification from national laboratories or universities before we can fully remove it from the wait-and-see category. Despite the need for further testing, Amprius appears to have a promising trajectory. The company is making significant strides towards mass production by establishing a sprawling 103-acre campus, which includes their existing 1.278 million square foot facility in Brighton, Colorado. This state-of-the-art factory is poised to substantially enhance Amprius's manufacturing capabilities, initially offering a capacity of 500 megawatt-hours with a potential for expansion of up to 5 gigawatt-hours within the current infrastructure. Their ambitious objective is to commence operations within the next few years, marking a significant milestone in the advancement of their groundbreaking battery technology. As mentioned earlier, Amprius isn't the only company finding success with silicon and nanotechnology. 1D's collaborated with GM and is also exploring nanotechnology solutions for silicon anode batteries. Together, they've developed the GM Ultium silicon anode battery. Sila Nano's nanotechnology has been incorporated into Whoop's wearable fitness tracker since 2021. Their enhanced batteries will become the standard in the Mercedes G-Class SUV starting in 2026. Additionally, Group 14 Technologies will supply silicon batteries for Porsche vehicles next year. All these companies are in the process of gearing up for mass production, which is always a good sign. In the near future, advancements in ultra-dense battery technology could pave the way for Tesla to incorporate this type of battery into their new line of electric vehicles, including the Model 2 Redwood, Tesla Van, and Tesla Bus. With Tesla's commitment to innovation and performance, integrating the advanced battery technology could propel their vehicles further in terms of efficiency and travel range per charge. The collaboration between Tesla and ultra-dense battery manufacturers could lead to a significant breakthrough in the electric vehicle industry, driving the development of clean and sustainable transportation worldwide. Will this ultra-dense battery change the world? It seems like we won't have to wait too long to find out. We hope you'll experience the utmost relaxation after watching this video. If you do, please hit the like button and join the Tesla Car World community by subscribing to our channel. Hit the notification bell icon and stay tuned for any fantastic videos coming your way. Your feedback and time are highly appreciated. Thanks so much for watching, and we look forward to seeing you soon. Until then, stay safe and enjoy.